Presented by CDG Training, this program is a comprehensive, scientifically rigorous course for agricultural professionals, environmental consultants, farm advisors, land managers, and policymakers. It's committed to the future of food, climate stability, and ecological resilience. Welcome to CDG Training's Agricultural Soil Health and Sustainable Farming Specialist course. This course is one of the most comprehensive, scientifically rigorous, and practically essential programs available for professionals committed to the future of food, climate stability, and ecological resilience. Soil health is the most critical environmental issue of our time. It supports 95% of our food and stores more carbon than all the world's vegetation and atmosphere combined. Yet, 33% of soil is already degraded, costing the global economy $10 trillion annually. Soil degradation is a global crisis with significant regional impacts. Africa, Asia, and Latin America are severely affected, with billions of hectares moderately to severely degraded, costing billions annually in agricultural productivity loss. The connection between soil health and food security is direct and quantifiable. A 1% increase in soil organic matter can significantly boost crop yields, while degraded soils can reduce yields by up to 50%. This is a food security necessity. The dynamic relationship between soil organic matter and crop yield is crucial. Increasing soil organic matter can dramatically enhance agricultural productivity, demonstrating the need for healthy soils to manage food security. Soil health is defined by its capacity to function as a living ecosystem. The 5 principles of soil health include minimizing disturbance, maintaining living roots, keeping soil covered, maximizing biodiversity, and integrating livestock. The 5 principles of soil health are assessed for their impact on various factors like soil organic matter, erosion reduction, and nutrient cycling. This integrated approach is more effective than single practices. From ancient Mesopotamia to the Dust Bowl of the 1930s, soil degradation has been a persistent issue. The Dust Bowl was a result of aggressive mechanical cultivation, highlighting the need for sustainable practices. Over 4 decades, sustainable and regenerative agriculture has evolved, emphasizing the importance of organic and regenerative practices. This shift is grounded in scientific research rather than promotional narratives. Comparing conventional and regenerative agriculture shows that regenerative practices lead to higher yields, better soil organic matter, and increased drought resilience, proving their long-term benefits. The global policy landscape for soil health is evolving with initiatives like the EU Farm-to-Fork strategy and USDA conservation programs, aiming to support sustainable farming practices and market incentives. Global investment in soil health and sustainable farming is essential, with billions allocated annually. This demonstrates the strategic importance of soil health as an international priority. This course is designed for farm advisors, environmental consultants, land managers, sustainability professionals, policy officers, and early career professionals, providing them with the knowledge to impact global sustainability. The course offers a structured learning journey across 15 chapters, covering foundational science, degradation threats, regenerative practices, climate and carbon, and professional development. The Soil Association in the UK exemplifies successful soil health transformation. Long-term monitoring shows higher organic matter and reduced soil microbial communities, proving the effectiveness of sustainable practices. Soil health is crucial for food security, climate stability, and ecological resilience. CDG Training equips you with the tools, frameworks, and confidence to transform agricultural systems for a sustainable future. Understanding soil science is crucial for sustainable farming. It involves studying composition, structure, and classification to manage soil health effectively. Jenny's equation highlights the 5 soil-forming factors: climate, organisms, relief, parent material, and time, each playing a vital role in soil development. The CLORPT model illustrates how different factors influence soil properties, emphasizing the complex interactions that shape soil characteristics. Soil texture, determined by sand, silt, and clay, is foundational for soil properties. The texture triangle helps classify soils for better management. The USDA Soil Texture Triangle categorizes soils into textural classes, aiding in understanding their agricultural and physical characteristics. Soil structure involves the arrangement of particles into aggregates, affecting productivity and management practices. Soil aggregate stability is linked to agricultural and environmental functions, influencing water retention and erosion resistance. Soil horizons reveal the history of soil formation, with each layer providing insights into soil properties and development. Comparing healthy and degraded soils shows the impact of management practices on soil function and productivity. Soil classification systems like USDA and WRB provide a framework for understanding soil types and their global significance. USDA soil orders highlight the global distribution and agricultural significance of different soil types, impacting land use decisions. Field diagnostic properties like color, consistency, and smell help assess soil health without laboratory tests. Water dynamics in soil are crucial for plant growth and management, affecting irrigation and water retention strategies. Soil organic matter is vital for soil health, influencing nutrient supply, carbon storage, and biological activity. Different fractions of soil organic matter affect management practices, emphasizing the need for tailored soil health strategies. Soil pH affects nutrient availability and crop growth, requiring careful management to maintain optimal conditions. The Rothamsted experiments provide valuable insights into long-term soil management and its effects on agricultural productivity. Soil is a dynamic system essential for agriculture, requiring careful management of its physical and chemical properties. A single teaspoon of healthy agricultural topsoil contains 1 billion bacteria, illustrating the incredible complexity and richness of living soil. This biological diversity is the engine driving agricultural productivity. The soil food web is a network of feeding relationships that drive nutrient flow. It includes primary producers, consumers, and higher organisms, each playing a crucial role in maintaining ecosystem balance. The agricultural soil food web showcases the flow of energy and nutrients, with energy inputs and ecosystem service outputs highlighting the efficiency of nutrient cycling and biomass distribution. Soil bacteria are the most abundant and metabolically diverse organisms, performing essential biochemical transformations. They play a vital role in nutrient cycling and agricultural productivity. The nitrogen cycle demonstrates biological transformations that enhance nitrogen availability. Management interventions can increase fixation and minimize denitrification, optimizing agricultural productivity. Soil fungi, particularly arbuscular mycorrhizal fungi, form a vast network that supports plant growth and soil structure. They play a critical role in nutrient uptake and ecosystem stability. Arbuscular mycorrhizal fungi enhance nutrient uptake and drought resistance, offering significant agricultural benefits. Their colonization is influenced by management practices, impacting yield retention. Earthworms transform soil properties, enhancing its structure and fertility. They are vital ecosystem engineers, contributing to nutrient cycling and soil health. Earthworm populations respond to management practices, influencing soil health and productivity. Their presence offers functional benefits, contributing to global soil ecosystem services. Protozoa and nematodes play a crucial role in nutrient cycling by grazing on bacteria and fungi. They are essential for maintaining soil health and supporting plant growth. Soil arthropods and mesofauna contribute to soil structure and nutrient cycling. They are indicators of soil health, reflecting changes in management practices. Biological community recovery is essential for transitioning from conventional to regenerative farming. This shift enhances soil health and resilience, supporting sustainable agriculture. The rhizosphere is a biologically active zone influenced by plant roots. It plays a critical role in nutrient cycling and supports diverse microbial communities, enhancing soil health. Biological nitrogen fixation offers a sustainable alternative to synthetic fertilizers. It enhances soil fertility and reduces environmental impact, supporting sustainable agricultural practices. The broad box of Rothamsted experiment highlights the impact of microbial communities on soil health. It demonstrates the potential for long-term agricultural sustainability through microbial management. Understanding, protecting, actively managing, and assessing soil organisms are crucial for sustainable agriculture. These practices enhance soil health and productivity, ensuring long-term agricultural success. Every crop that grows in agricultural soil is engaged in a complex chemical conversation with its environment. This involves nutrient cycling, cation exchange, and pH dynamics, all crucial for maintaining soil fertility. Let's explore these essential processes. Plants require 17 essential mineral nutrients for growth and reproduction. These nutrients are divided into primary and secondary macronutrients, as well as micronutrients, each playing a vital role in plant health and development. Understanding the functions, sources, and deficiency symptoms of essential plant nutrients is key to effective soil management. This knowledge helps in diagnosing and addressing nutrient deficiencies to ensure optimal plant growth. Cation exchange capacity, CEC, measures a soil's ability to hold onto essential nutrients. It is influenced by permanent negative charges and pH-dependent charges, affecting nutrient retention and soil fertility. Managing CEC involves understanding its sources and how it affects nutrient retention. By increasing soil organic matter, we can enhance CEC, leading to better soil structure and fertility. Soil pH is a critical factor in soil chemistry, influencing nutrient availability and biological activity. It determines the solubility of nutrients and the activity of soil enzymes, impacting plant health. The availability of plant nutrients is highly dependent on soil pH. Different pH levels create zones of nutrient availability or deficiency, affecting plant growth and soil health. Soil organic matter chemistry involves the formation and decomposition of humus, which is crucial for nutrient supply. Understanding these processes helps in managing soil fertility effectively. Phosphorus chemistry in soil is complex, involving various pools and transformation rates. Proper management of phosphorus is essential for maintaining soil fertility and supporting plant growth. Effective phosphorus management involves understanding its pool sizes and transformation rates. This ensures that phosphorus is available for plant uptake, enhancing growth and productivity. Soil testing is essential for nutrient management planning. It helps determine the chemical properties of soil, guiding the application of fertilizers and amendments to optimize soil fertility. The UK Nutrient Management Guide provides a soil index system to balance crop yield with environmental protection. It offers recommendations for nutrient applications based on soil type and condition. Secondary nutrients and micronutrients are vital for soil fertility management. Proper management strategies ensure that these nutrients are available to plants, supporting healthy growth and development. Soil contamination from heavy metals and organic pollutants poses a challenge to soil fertility. Understanding the sources and implementing remediation strategies is crucial for maintaining soil health. The Broadbach experiment provides valuable insights into nutrient chemistry over 180 years. It highlights the importance of long-term soil management practices in maintaining soil fertility and productivity. Soil chemistry is the foundation of soil fertility, guiding nutrient management and soil health restoration. Mastering these principles enhances agricultural productivity and environmental sustainability. Soil degradation significantly reduces ecosystem services and agricultural productivity. It's a complex issue involving various dimensions of soil health. The FAO estimates that 23 hectares of productive land are lost every minute due to degradation. Let's explore the major categories, interactions, and training objectives to combat this challenge. Water erosion is the most significant form of soil degradation, affecting 56% of total soil degradation worldwide. It impacts 1.1 billion hectares of agricultural land. Understanding the processes of detachment, transport, and deposition is crucial to addressing this crisis. Erosion rates vary globally, influenced by factors like ground cover and regional practices. Understanding these rates and their controlling factors helps in developing effective soil conservation strategies. Wind erosion is a significant form of soil degradation, especially in semi-arid regions. It involves processes like surface creep, saltation, and suspension, which contribute to the loss of topsoil and agricultural productivity. Topsoil loss directly affects agricultural productivity. Long-term assessments show the need for effective soil conservation practices to maintain soil health and ensure sustainable agricultural output. Soil compaction reduces soil volume and pore space, affecting root growth and water infiltration. It's a major issue in agriculture, leading to significant yield losses annually. Understanding its causes and effects is essential for effective management. Agricultural machinery contributes to soil compaction, affecting crop yield. Understanding the pressure exerted by different machines and its impact on soil structure is crucial for developing better management practices. Soil salinization affects approximately 833 million hectares globally, impairing plant growth and soil structure. Understanding primary and secondary salinization processes is key to managing this issue effectively. Soil salinization is a global issue, with significant impacts on agricultural productivity. Understanding the extent and crop tolerance levels helps in developing strategies to mitigate its effects. Remediating soil compaction involves mechanical intervention, biological management, and preventive measures. Techniques like deep loosening tillage and controlled traffic farming are effective in restoring soil health. Soil degradation processes are interconnected, creating self-reinforcing feedback loops. Understanding these interactions is crucial for developing effective soil management strategies. Acidification management involves using alkaline liming materials to correct soil pH. Understanding the types of lime and their application is essential for effective soil management. Soil contamination involves harmful chemical compounds affecting health and productivity. A structured assessment and remediation process is essential for addressing this issue effectively. The Great Plains Conservation Program is a historical example of successful soil conservation. Established in 1956, it demonstrates the importance of policy commitment, farmer engagement, and landscape-scale action in soil recovery. Soil degradation is preventable through understanding and managing its causes. Prioritizing prevention and effective management strategies can significantly reduce the impact of soil degradation on agriculture and the environment. The fundamental productivity paradox of modern agriculture is that decades of investment in simplifying farming systems, reducing crop species, eliminating livestock integration, removing hedgerows, has not improved long-term productivity. Instead, it has often led to increased vulnerability to pests, diseases, and climate change. Simplification destroys biological diversity and natural capital, which are crucial for sustainable productivity. The solution lies in diversified farming systems, which can enhance resilience and productivity across all dimensions. Cover crops are plant species grown specifically to cover the soil between harvests. They are the most rapidly adopted and most widely applicable tool for improving soil health. Cover crops provide surface protection, enhance nitrogen fixation, support pollinator habitats, and improve soil structure. They also play a critical role in weed suppression, which is increasingly important as herbicide resistance spreads. Meta-analyses of 50 studies reveal that cover crops significantly improve soil health indicators. They reduce erosion by 60%, decrease nitrogen fertilizer use by 22%, and increase weed biomass by 49%. These benefits translate into a 3% increase in crop yield, showcasing the tangible advantages of integrating cover crops into farming systems. Selecting the right cover crop species or mixes is crucial for achieving specific objectives. Grasses and cereals protect soil and suppress weeds, legumes fix nitrogen, and brassicas improve soil structure. An optimal mix strategy involves combining these species to complement each other, enhancing overall soil health and productivity. This matrix helps in selecting cover crop species based on their functional performance across various objectives like soil building, nitrogen management, and pollinator habitat. By understanding these functions, farmers can tailor their cover crop strategies to meet specific goals, optimizing their farming systems. Crop rotation involves growing a planned sequence of different crops on the same field in successive seasons. It is one of the oldest and most universally validated soil health practices. Rotation benefits include biological, chemical, and physical improvements, such as breaking pest cycles, diversifying root structures, and enhancing habitat conditions. Diverse crop rotations significantly enhance soil health and productivity. By comparing various rotation schemes, it's evident that diversity reduces disease pressure and weed seed banks, while also lowering input costs. This approach leads to more resilient and sustainable farming systems. Green manures and undersown crops are incorporated into the soil to build biological fertility. They reduce nitrogen dependence and build organic matter, enhancing soil health. These practices are crucial for maintaining crop productivity and are increasingly recognized for their role in sustainable agriculture. Effective nitrogen management is essential for sustainable farming. Biological sources of nitrogen improve nitrogen use efficiency by 67% and reduce leaching losses by 45%. This not only enhances soil health but also reduces costs, making it a more sustainable option compared to synthetic sources. Intercropping involves growing multiple crop species together, enhancing resource use efficiency and ecological balance. This practice supports biodiversity and improves resilience against pests and diseases. By carefully selecting species and managing planting times, farmers can optimize the benefits of intercropping. Diversified farming systems balance profitability with soil health. By integrating various crops and practices, farmers can achieve higher income resilience and improved soil conditions. This approach not only enhances farm sustainability but also contributes to long-term ecological health. Perennial crops, like Kernza perennial wheatgrass, offer ecological benefits by maintaining soil structure and enhancing carbon sequestration. These systems are resilient to drought and support long-term soil health, making them a valuable component of sustainable agriculture. The Countryside Stewardship Scheme in the UK demonstrates the benefits of cover crop adoption. Financial incentives and measurable soil health improvements have led to increased adoption rates. This example highlights the role of policy and community engagement in promoting sustainable farming practices. Diversification in farming systems is not just a theoretical concept, it's a practical necessity. By integrating cover crops, crop rotation, green manures, intercropping, and perennials, farmers can achieve multiple benefits, including enhanced resilience, productivity, and ecological alignment. This comprehensive approach is supported by overwhelming scientific evidence and offers a sustainable path forward for agriculture. There is a profound and transformative shift in agricultural philosophy embedded in the distinction between feeding crops directly through soluble mineral inputs and feeding the soil biological fertility that feeds the crop through natural processes. Composting, organic matter, and biological soil amendments are the practical tools through which this philosophy becomes farming practice, providing the carbon-rich organic materials and biological inoculants that feed soils, build organic matter, improve structure, and progressively restore the biological fertility that intensive agriculture has depleted. Understanding the carbon cycle in agricultural soils is crucial. It involves the processes through which carbon enters the soil from plant residues and organic inputs, transforming through biological decomposition and chemical stabilization, and returns to the atmosphere through respiration and combustion. This cycle is essential for maintaining soil fertility and making credible claims about soil carbon sequestration and climate change mitigation. Carbon remaining and nitrogen availability vary over time, revealing the contrasting decomposition rates between organic amendments. This understanding helps in optimizing nutrient release for crop uptake and soil health. Composting is the controlled decomposition of organic materials under specific conditions. It involves three distinct temperature phases: mesophilic, thermophilic, and maturation. Each phase plays a critical role in breaking down organic matter and stabilizing nutrients, ensuring high-quality compost. Temperature is a vital quality determinant in the composting process. Monitoring temperature and quality progression ensures the material is progressing toward maturity and pathogen reduction, crucial for safe and effective compost application. Farmyard manure and slurry are valuable byproducts of livestock enterprises. Proper management and application can significantly enhance soil health and fertility, making them essential components of sustainable farming practices. Different organic amendments have varying impacts on soil health. Understanding these effects helps in selecting the most suitable amendment for specific agricultural needs, optimizing crop yield and soil fertility. Biochar is a highly stable carbon-rich material produced by the thermal decomposition of organic biomass. It represents one of the most intriguing and commercially promising emerging soil amendment categories, combining ancient wisdom with modern science. Biochar production parameters significantly influence its effectiveness in enhancing soil fertility and crop yield. Understanding these parameters helps in optimizing biochar application for maximum agricultural benefits. Microbial inoculants are commercial products containing concentrated populations of beneficial soil microorganisms. They are designed to enhance biological processes in soil, promoting plant growth and soil health. Selecting the right biological soil amendment involves understanding the specific needs of the soil and crops. A decision framework helps in making informed choices, ensuring optimal soil health and productivity. Vermicomposting is the processing of organic materials through the digestive systems of earthworms. It generates one of the most biologically active soil amendments, enhancing soil fertility and plant growth. The DOK trial is a long-term experiment that has provided valuable insights into organic matter management. It highlights the benefits of organic amendments in improving soil health and fertility over decades. Composting, organic matter management, and biological amendments are not supplementary additions to an otherwise chemical farming system. They are the primary tools through which the living soil is fed, the biological community is sustained, and the long-term biological capital of agricultural land is either built or depleted. Water and soil exist in a relationship of mutual dependence so fundamental that neither can be understood, managed, or protected in isolation from the other. Soil isolation from the other. Soil stores water, filters it, regulates its flow through landscapes, and makes it available to plants and animals. Water drives the weathering and chemical reactions that produce the soil, transports nutrients, and constitutes 25 to 40% of the volume of a well-structured soil. The relationship between soil and water, how soil holds water, releases it to plant roots, transmits it through the profile, and exchanges it with the surface atmosphere, is the foundation of every agricultural water management professional must understand. Understanding soil water retention and the effect of texture and organic matter on plant-available water is crucial for optimizing crop yield and ensuring efficient water use. Water infiltration is the process through which water enters the soil surface and moves through the soil profile. It is perhaps the single most important hydrological function of agricultural soils and the process most directly and dramatically affected by soil health management decisions. The impact of management systems on soil infiltration rate and rainfall partitioning is significant. Different farming systems and management practices can greatly influence how water is absorbed and utilized by the soil. Irrigation is practiced on approximately 330 million hectares globally, accounting for 20% of cropland producing 40% of global food supply. The efficiency with which irrigation water is applied varies enormously between systems. A comparison of irrigation systems across application efficiency, soil structure protection, salinization risk, and capital cost shows the varied advantages and disadvantages of each system. Irrigation scheduling is the determination of when to irrigate and how much water to apply. It is the management practice that most directly determines irrigation water use efficiency, reduces environmental impacts, and minimizes the risk of failures of over-irrigation and under-irrigation. Soil moisture conservation strategies can lead to significant water savings over the growing season, enhancing productivity and reducing costs. Drainage management, the installation, maintenance, and management of systems that remove excess water from the soil profile to prevent waterlogging, is one of the most technically complex aspects of agricultural water management in humid temperate climates. Agricultural runoff, water flowing off farmland carrying dissolved nutrients, suspended sediments, pesticides, and pathogens, is the leading cause of water quality degradation in freshwater bodies globally. A holistic water management approach that considers the potential of combining soil health management with targeted buffer strips and water retention strategies can yield significant benefits. Deficit irrigation, the deliberate application of less water than full crop evapotranspiration requirements during specific periods, represents a fundamentally different management philosophy from traditional irrigation that seeks to fully eliminate crop water stress. The Murray-Darling Basin, covering approximately 1 million square kilometers of southeastern Australia and producing approximately 40% of Australian food and agricultural exports, provides one of the most extensively documented case studies of integrated agricultural water management and the complex responses required to balance competing demands. Water management and soil health management are not separate disciplines that occasionally intersect. They are two dimensions of the same integrated science of how soil, water, biology, and agricultural production function as a system. Integrated pest management, IPM, is a holistic approach that combines pest suppression with reduced chemical inputs, focusing on working with nature rather than against it. This chapter explores the economic and health benefits of IPM, emphasizing its role in sustainable agriculture. Soil biological communities play a crucial role in pest suppression by maintaining a diverse ecosystem that naturally controls pests. This slide highlights the importance of healthy soil biology and its mechanisms in reducing pest populations. The recovery of soil biological communities after stopping pesticide use is significant. This graph illustrates how soil health improves over time, leading to better pest management and ecosystem balance. The scientific framework of IPM includes 8 principles, from prevention to evaluation, ensuring effective pest management while minimizing risks and environmental impact. Economic thresholds in IPM help determine when pest control actions are necessary, optimizing resource use and minimizing unnecessary interventions. Biological control harnesses natural predators and competitors to manage pest populations, offering a sustainable alternative to chemical methods. Farm landscapes support beneficial insects by providing habitats that enhance pest suppression, demonstrating the importance of ecological balance in agriculture. Herbicide resistance is a growing challenge, requiring integrated weed management strategies to maintain effective control and protect crop yields. The global spread of herbicide resistance necessitates a strategic response, combining various management practices to sustain agricultural productivity. Reducing fungicide use and managing biological diseases are essential for sustainable agriculture, focusing on host plant resistance and biological fungicides. Neonicotinoids impact pollinators and soil health, highlighting the need for careful management and regulation to protect ecosystems. Adopting IPM leads to positive economic and environmental outcomes, enhancing soil health and reducing resistance incidences. The leaf mark exemplifies successful integration of IPM and sustainable farming, showcasing improved productivity and environmental stewardship. IPM is essential for balancing environmental goals with agricultural needs, ensuring effective pest regulation, productivity, and compliance with global standards. Trees, soil, and the long view, exploring how the deliberate integration of woody perennial vegetation into farming landscapes transforms soil health across timescales that annual cropping systems fundamentally cannot reach. Agroforestry encompasses an extraordinary range of land use systems, from Southeast Asia's complex multi-strata forests to Northwest Europe's hedgerows. These systems are defined by their spatial arrangement and temporal management, offering diverse ecological benefits. Agroforestry systems cover 3.2 billion hectares globally, offering significant carbon benefits. They consistently outperform monoculture systems in carbon sequestration, especially in tropical regions, enhancing both productivity and environmental health. Root systems in agroforestry create a three-dimensional network that enhances soil health by accessing deep nutrients, redistributing water, and depositing carbon at various depths, fostering a robust underground ecosystem. Agroforestry systems demonstrate superior root biomass distribution compared to annual crops, with deeper and more extensive root systems that enhance soil structure and nutrient cycling, supporting sustainable agriculture. Alley cropping integrates trees with crops, optimizing land use and enhancing soil health. By selecting specific tree species and monitoring soil health, this system improves productivity and resilience against environmental stresses. Over 30 years, alley cropping shows significant improvements in soil health and financial returns, outperforming monocultures. Carbon sequestration accelerates and financial gains increase, proving its long-term viability. Silvopasture integrates trees into grazing systems, offering substantial soil health benefits. It enhances carbon sequestration, modifies microclimates, and supports livestock welfare, making it a compelling agroforestry practice. Silvopasture significantly outperforms open pasture in soil health metrics, with improvements in surface and deep soil organic carbon, infiltration, and biodiversity, demonstrating its ecological advantages. Hedgerows and farm woodlands are vital for landscape soil health, providing ecological infrastructure and influencing soil health zones. They support biodiversity and enhance soil organic matter, crucial for sustainable farming. Financial incentives and policies are crucial for agroforestry adoption. Support from stewardship payments, carbon markets, and integrated advisory approaches help overcome initial challenges, promoting sustainable land management. Integrating agroforestry enhances soil health and biodiversity at a landscape scale. It increases soil organic matter, earthworm populations, and biodiversity, creating a resilient agricultural ecosystem. Wakelands Agroforestry in Suffolk, England, exemplifies successful agroforestry with improved soil organic matter, earthworm populations, and water infiltration, showcasing its ecological and scientific legacy. Agroforestry represents the deepest and most ecologically powerful soil building strategy available to agriculture, promoting long-term sustainability through biodiversity and carbon sequestration, transforming farming landscapes. Agriculture plays a unique role in the global climate crisis, being both a significant contributor to greenhouse gas emissions and a promising solution for carbon sequestration. This chapter delves into the science, methodologies, and policies surrounding soil carbon management, highlighting its potential to mitigate climate change. The global carbon cycle has been altered since the Industrial Revolution, with agriculture playing a crucial role. Terrestrial soils store vast amounts of carbon, and their management can significantly influence atmospheric CO2 levels. Understanding and managing these carbon pools is essential for climate stability. Agriculture contributes significantly to global greenhouse gas emissions. This breakdown shows the sources and potential reduction targets, emphasizing the need for strategic interventions to meet climate goals. Soil carbon sequestration involves complex biological and chemical processes. Key mechanisms include carbon input, microbial transformation, stabilization, and saturation limits. Understanding these processes is vital for effective carbon management. Different management practices yield varying rates of soil carbon sequestration. This evidence highlights the potential of practices like cover cropping and agroforestry to enhance carbon storage in soils. Nitrous oxide, with its high global warming potential, is a critical greenhouse gas. Understanding its emission factors and management strategies is essential for reducing its impact on climate change. Agricultural practices contribute to N2O emissions, but targeted management can significantly reduce them. This slide explores various mitigation pathways and their potential to lower emissions. Methane emissions from livestock are a major concern. Effective management strategies, including dietary modifications and selective breeding, can significantly reduce these emissions. Technological advancements offer promising solutions for reducing methane emissions from livestock. This slide examines various mitigation technologies and their effectiveness. The 4 per mil initiative aims to increase global soil carbon stocks, offering a potential solution to climate change. This slide discusses the scientific critique and the initiative's potential impact. Voluntary carbon markets are emerging as a financial mechanism to incentivize agricultural soil carbon sequestration. This slide explores various standards and their role in promoting sustainable practices. Assessing the economic viability of agricultural carbon markets is crucial for their success. This slide provides insights into the financial aspects and potential benefits for farmers. Australia's Emissions Reduction Fund is a leading example of government-supported soil carbon projects. This initiative highlights the potential for large-scale carbon sequestration and its economic benefits. Soil carbon sequestration and agricultural greenhouse gas management are essential for climate stability and agricultural viability. Mastering the science, measurement, and market frameworks is crucial for sustainable farming. Understanding soil degradation begins with effective measurement and monitoring. This chapter explores the core challenges and professional shifts necessary for long-term soil health solutions. Soil health assessment requires a holistic approach, integrating physical, biological, and chemical indicators. This framework helps in understanding soil functions and limitations. The Cornell Soil Health Assessment provides a comprehensive scoring framework, helping farmers prioritize management actions based on various soil health indicators. Field observation skills are crucial for assessing soil health. Techniques like the soil pit, Vest spade test, and slake test provide immediate and practical insights into soil conditions. Rapid farm-scale evaluation involves visual surveys, spade tests, and pentrometer readings, offering a quick and effective soil health assessment protocol. Laboratory soil analysis provides precise data for management decisions. Proper sampling and timing are critical for accurate results and recommendations. Biological indicators offer insights into soil health. Understanding their methods and applications enhances monitoring and management strategies. Accurate soil carbon measurement is essential for carbon credits. It requires precise sampling and modeling to distinguish management-induced changes from natural variability. Effective soil carbon monitoring involves strategic sampling design and statistical precision to ensure reliable data for management decisions. Digital soil mapping combines technology and data analysis to enhance precision soil management, offering a complementary tool to traditional sampling methods. Long-term soil health monitoring builds a robust evidence base, essential for sustainable farming practices and informed management decisions. A structured framework for long-term farm soil health monitoring includes annual, 3-year, and 5-year cycles, optimizing information for management decisions. France's indicator of soil quality exemplifies a national effort in soil health assessment, highlighting the importance of structured monitoring and management. Measurement is crucial for credible soil health practices. It supports demonstration, targeted interventions, and evidence-based decision-making. From farm gate to policy table, the most technically sophisticated soil health knowledge operates within a broader context of agricultural policy frameworks and environmental schemes. No agricultural soil health professional can deliver their full potential without a thorough understanding of the policy landscape that shapes the economic conditions, regulatory requirements, and incentives within which farming decisions are made. The Common Agricultural Policy, or CAP, is the European Union's central agricultural governance framework. Established in 1962, CAP has undergone significant reforms, most recently in 2023, to address environmental sustainability and climate change. These reforms include eco-schemes, GAEC conditionality, and a penalty framework, all aimed at promoting sustainable farming practices across Europe. The CAP 2023-2027 budget allocates €387 billion, with 27% directly supporting eco-schemes and soil health initiatives. This budget reflects a significant commitment to environmental sustainability, with mandatory eco-schemes and soil health standards being implemented across member states. The UK's Environmental Land Management Scheme represents a significant shift in agricultural policy post-Brexit. It emphasizes sustainable farming incentives, local nature recovery, and landscape recovery, aiming to deliver environmental outcomes through tailored land management practices. The Sustainable Farming Incentive outlines meaningful financial support for soil management improvements. Payment rates are designed to encourage adoption of soil health practices, with examples showing potential earnings for farmers who implement these beneficial practices. The USDA administers the world's largest agricultural conservation programs, investing approximately $6 billion annually to support practices that improve soil health, water quality, and wildlife habitat. Programs like EQIP, CSP, and CRP provide financial and technical assistance to farmers. Meta-analysis of European and North American programs reveals that multi-year schemes with bundled practices are most effective. These schemes significantly improve soil health outcomes, confirming the economic case for environmental policy integration. The farm-to-fork strategy aims to transform the EU food system by 2030, targeting reductions in pesticide use, nutrient loss, and fertilizer use, while increasing organic farming. This strategy supports sustainable food systems and healthier diets. Major agribusinesses are increasingly committing to specific soil health requirements, with financial incentives and supply chain coverage. Companies like General Mills and McCain Foods are leading the way in sustainable sourcing and regenerative agriculture. Mandatory soil health standards are emerging globally, with countries like New Zealand and England leading the way. These standards aim to maintain soil health above minimum thresholds, ensuring sustainable agricultural practices and environmental protection. The food system is an interconnected network, linking soil health to production, processing, and consumption. Sustainable Development Goals emphasize the importance of soil health in achieving clean water, climate action, and life on land. Integrating policy with farm management responses is crucial for achieving desired soil health outcomes. This approach ensures that policy initiatives translate into practical actions on the ground, leading to improved soil health and sustainability. Landscape Enterprise Networks, or LENs, are innovative models that connect ecosystem services with financial incentives. These networks facilitate collaboration among water companies, local authorities, and conservation organizations to deliver sustainable land management. Agricultural policy and food system governance are critical for soil health practitioners. Professionals must combine technical soil science expertise with policy literacy and market awareness to effectively engage with stakeholders and navigate the complex soil health landscape. You've reached the final chapter of one of the most comprehensive and scientifically rigorous professional certification programs available in agricultural soil health and sustainable farming. This program has guided you from foundational soil science through advanced management techniques, preparing you for a significant professional impact. The demand for agricultural soil health expertise is rapidly increasing, driven by regulatory changes, corporate sustainability goals, and evolving carbon markets. This creates a wealth of opportunities across various sectors, making it an exciting time to be involved in this field. Soil health specialists are in high demand, with roles offering competitive salaries and growth opportunities. The career trajectory is promising, reflecting the increasing importance of sustainable practices in agriculture. Soil health expertise opens doors to diverse career paths, from advisory roles to corporate sustainability and public sector positions. Each path offers unique opportunities to make a meaningful impact on agricultural practices and policies. Career progression in soil health involves stages from foundational learning to senior roles, with opportunities for specialization and leadership. Accelerators like certifications and networking can enhance your career trajectory. Professional certifications validate your expertise in soil health, offering recognition and enhancing your career prospects. Various certifications cater to different aspects of soil health, ensuring comprehensive professional development. Understanding the requirements and value of different certifications helps tailor your professional development to your career goals. Certifications provide market recognition and are crucial for career advancement in soil health. Building a strong professional profile involves publishing research, presenting at industry events, and participating in policy development. These activities enhance your visibility and credibility in the field. Balancing professional visibility activities with time investment is key to maximizing career impact. Prioritizing activities that align with your career goals ensures effective professional growth. Staying current in soil health requires ongoing education and adaptation to new technologies and methodologies. Continuous professional development is essential for maintaining expertise and advancing your career. The future of soil health practice involves regulatory embedding, technological transformation, and multi-outcome integration. These trends are shaping the profession, offering exciting opportunities for innovation and impact. Emerging opportunities in soil health are driven by technological advancements and new professional roles. Staying informed about these trends positions you to take advantage of future career prospects. Enrolling in a professional certification course offers flexibility and comprehensive learning, preparing you for a successful career in soil health. The program is fully online, allowing you to study at your own pace. The learning experience is designed to be flexible and accessible, with online materials and examinations. This approach allows you to balance professional development with other commitments seamlessly. A practical example of career transformation through soil health expertise highlights the journey from conventional agronomist to recognized specialist. This transformation underscores the value of certification and expertise in advancing your career. The certification in soil health is not just an educational journey but a pathway to professional impact. It equips you with the skills to assess, design, and implement sustainable practices effectively. Enrolling in the certification program is the first step towards a rewarding career in soil health. With comprehensive chapters and flexible learning, you can achieve significant professional growth and earning potential. CDG Training is your partner in achieving professional excellence in soil health. With a focus on scientific rigor, professional impact, and ongoing partnership, we support your journey towards becoming a leader in sustainable farming.